All right, good morning. This is Miss Triangle. And we are working on section 2.2, which kind of covers inductive and deductive reasoning. It's kind of a long section, it's kind of a challenging section, but what we're going to focus on this year is kind of exposing and getting everyone kind of an introductory level of inductive and deductive reasoning and some laws of logic versus feeling like you understand this 1000% and are an expert. So we want you to get kind of an overview. So keep that in mind. So start by putting the date and today's topic, 2.2, inductive and deductive reasoning, in the top right of your paper. Next, you're going to write your essential question or EQ. How can you use reasoning to solve problems? How can you use reasoning and logic to solve problems? We're on learning target 2B because this is chapter 2. I can identify and use inductive and deductive reasoning to solve problems. So we want to know which type of reasoning we're using and then also use that to answer and solve problems. So if you need to pause the video to get this, please do so. Otherwise, I'm going to move on. All right, here's some vocabulary words. Conjecture. So it's kind of like a theorem, except for it's an unproven statement. So a theorem is proven. You can do a formal proof for that. Conjecture is something that's not proven, but you base it on observations. So, for example, maybe that it rains a lot in April. So can we do a formal proof? Perhaps, but if we just notice outside, wow, it's raining and it's April 1st, it's 3rd, 6th, if we just kind of observe, wow, it's really rainy, we might say a conjecture, it rains a lot in April. So that's a conjecture. So it doesn't mean that it's like a bad statement or an untrue statement, it's just not formally proven. Okay? All right, our second vocabulary word is inductive reasoning. So for inductive reasoning, you find a pattern by looking at specific cases, so specific examples, and then you find a general pattern. Specific examples, and then you find a general pattern. So, for example, with inductive reasoning, you kind of make an observation. So you make a specific example. So maybe you notice, wow, I eat peanuts and I get a rash. Okay, then you might think, maybe I'm allergic, and you might come to the general conclusion that I'm allergic to peanuts based on your specific observations of getting a rash. So that would be inductive reasoning, sort of seeing specific examples and making a general conclusion. Okay, a counterexample is a really nice way of doing a proof because basically you just find something false. Because I think I said in example or in lesson 2.1, to be true, something has to be always true. So if it's true 9 out of 10 times, it's a false statement. So a counterexample, you just find something false. So for example, of a counterexample, there might be a statement such as, all girls have long hair. I could show or prove that that's a false statement by finding one person who identifies as a girl with short hair. That would be a counterexample, and that would be enough to prove that that's a false statement that all girls have long hair. All right, example problems. And so we're going to kind of focus on counterexamples and inductive reasoning to start, and we'll work on deductive the second half of the examples. So set up your examples, all right? And the question here is, how do we use inductive reasoning? So how do we use that to solve problems? So remember, going from specific to general. So first, in example 1, it says describe the pattern, then sketch the fourth figure. So let's just look and see what we notice. We have a circle broken into 2 parts with 1 shaded. Here we have a circle broken into 4 parts with 1 shaded. Here we have a circle broken into 6 parts with 1 part shaded. So I notice that it's kind of adding 2 each time. I'm adding 2 sections to my circle. So for the fourth one, let's go ahead and make a circle that's broken into 8 parts. And then let's go ahead and shade the top left spot here, 1 spot. Okay? So I used specific examples to come up with the fourth figure. And the pattern, describing the pattern, basically we're adding 2 sections, adding 2 sections to circle each time. That's the pattern. All right, number 2, same thing. You're getting 3 and you're getting 3 figures. You're going to draw the 7th picture, the 7th diagram, and you're going to describe the pattern that you see. Okay, so it looks like we're adding a row each time. And I notice the bottom row. Here the bottom row has 1. The bottom row has 2. Here the bottom row has 3. So to describe the pattern, I would say the last row has the same number, I'm going to use the number symbol, has the same number of circles as the figure. So figure 1, the bottom row has 1 circle. Figure 2, the bottom row has 2. Figure 3, the bottom row has 3. And so it says draw the 7th figure. I don't need to draw 4, 5, and 6 if I see the pattern. So for the 7th, there's going to be a lot of circles. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 1. And that is the 7th figure. All right, let's move on. All right, question or example 3. Numbers such as 3, 4, and 5 are called consecutive integers. Consecutive integers, that means they're in a row. Make and test a conjecture or an observation about the sum, that means you're adding the sum of any 3 consecutive integers. So let's try some stuff out. Let's start with 3, 4, and 5. The sum of 3, 4, and 5, so 3 plus 4 is 7, plus 5 is 12. Okay, let's try some other ones. Let's try 1, 2, and 3. Let's try small numbers. I don't really feel like adding huge numbers. Let's try 2, 3, and 4. 5, 9. Okay, what else? 4, 5, and 6. 5, 6, and 7, and we'll see if we can find a pattern. So if I add 4, 5, and 6, I get 15. Here I get 18. So pause the video, think about it. Do you see any patterns? If you're not seeing a pattern, I'm going to give you a little hint. I'm going to do a little highlighting. Let's look at the middle number. These are not quite in order. And let's look at the answer, the sum. Is there any pattern you're noticing between these numbers, between 4 and 12? How can you get from 4 to 12? How about 2 to 6? Now, if you said add 8 for 4 to 12, that's true, okay? But 2 plus 8 is not 6, so the pattern is not adding 8. So is there another way to get from 4 to 12 that would also work from getting 2 to 6, 3 to 9, 5 to 15, 6 to 18? Hopefully you're saying you're tripling or multiplying by 3. Okay? So let's make a conjecture. The sum of 3 consecutive integers is 3 times the middle number. And if you don't believe me, you can try out other numbers, bigger numbers in the 20s or 30s, okay? But this, we used inductive reasoning. We did specific examples to find a pattern, to come up with a general pattern. So that is inductive reasoning. Okay, a student makes, for example 4, you can summarize example 3 and example 4, so there should be something written down, okay? But you can summarize. A student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. So what is the conjecture? The sum of 2 numbers is always more than the greater number. The sum of 2 numbers. So let's try some stuff out. If we add 2 numbers, 1 plus 2, that equals 3. 3 is bigger than 1, and 3 is bigger than 2. So that's not a good counterexample because that's true. Okay, let's try something else. 2 plus 3 is 5, and 5 is bigger than 2, and 5 is bigger than 3. So it seems true. We know there's got to be a counterexample because the example says that. So it looks like with positive numbers, it's working. Why don't we try a negative number and see if that would work? So how about 5 plus negative 2? 5 plus negative 2 is 3, and look at that. 3 is not bigger than 5. 3 is smaller than 5. So here's a counterexample right here. If I use the numbers 5 and negative 2, 5 and negative 2, my sum is 3. 3 is not greater than 5. So I have disproven the statement by coming up with a counterexample. And that would work for any negative number, by the way. All right, number 5, make and test a conjecture about the sum of any 5 consecutive integers. Okay, we're actually, sorry if you wrote this down, I think we're going to go ahead and skip number 5, example 5, just because this section gets very long. Okay, for 6, or we'll rename this as 5, the value of x squared is always greater than x. We want to find a counterexample. Find a counterexample. So I always just usually start with number 1. So let's say x is 1. X squared, or 1 squared, equals 1. So right there, I already have a counterexample. Because if x is 1, 1 squared is 1, and 1 equals 1. 1's not greater than 1. So that's already a counterexample. Perfect, I'm done. Now, if I had tried something else that didn't work, like 2, 2 squared is 4, and 4 is greater than 2, then I would just have to try something else. Okay? So you might not get it on your first try like that, and that's okay.